Hello and welcome to another free code session. My name is Jason Bach, and in this episode I'm going to be talking about Advent of Code 2022, the work that I did on it, how I solved the problems, and my overall feelings and experience about doing Advent of Code this year. So as you can see right here, I've got the page up for Advent of Code. It's the site is adventofcode.com, and there's been numerous iterations of this event. If you go to the events link, you'll see that it's been going on since 2015. Essentially, it's an advent calendar, which if you don't know what an advent calendar is, it's something that people do as like a holiday tradition around the winter time. You have a calendar that is like this physical thing, typically, and they have little doors on them. And so you open up day one, there's a prize in there. Day two, there's a little prize or a little piece of candy or something like that, and you open up every day as you go up to day 25. And so this is every day you get a new problem that is actually in two parts, and you have to solve each one, and then if you do, you get 2 gold stars. As you can see here, I've done all 25 days, and so I get this little extra animation at the top with the balloons being freed. There's a story that goes along with the whole advent calendar that interweaves with these problems that you have to solve. So that's what this Advent of Code calendar is. I've heard about this. I've never done it before, but this year somebody on my team said, hey, maybe we should do this. Anybody done this before? I've tried this once. Anybody want to try it again? And I said, sure, why not? So I went through all the problems and was able to solve them. Some of them were easier than others. That's what I'm going to be talking about in this episode, what my experiences were with these. The one thing I want to stress right off the top, though, is speaking of stress, you'll see that there's a leaderboard here, and this shows you how fast people were able to solve the problems. I really feel like that's not a thing to focus on. If you want to, that's great. I'm not going to criticize people who do, but I got a lot more out of this by trying to solve the puzzles, try a couple different things and see what works and what doesn't, than it was to simply try to solve this as fast as I could. There were a couple times where I did do that. I'll share that as I go through the problems, and one time did not work out well at all. Primarily because the person that runs this, which you go to the about, that's Eric Wastel, I think that's how you say the name. Every day that a set of problems or parts are opened up is around 11 p.m. my time. And he said that he has to pick one time that works best for him in case problems come up or issues are occurring. And I get that. But that made it hard for me at that late a time, I'm an early riser these days, to have any brain power left to focus on these. And I'm also a little bit more competitive, mostly with myself, when I get into things like this, and that was frustrating me. One day I tried to do that. People solve these really fast too. I don't know how they do that. And I said to myself, again, it's the journey, it's about learning, and it's about the experience. It's not about trying to be on a leaderboard. So I'm going to go through all the problems now, primarily focusing on what I did in the code, which I use C#. I also have in my repository, which is in a link in the description, a answers file. I highly recommend that you don't just go through that and try to go through this Advent of Code calendar and say, oh, I solved them all. That's missing the point. I primarily have those answers there just because if I ever wanted to do something where I'm playing with the problem and I don't necessarily want to have the code up here to see that I get the answer right. Also, if I wanted to write these as also tests, then I need the answer there anyway in the test to show am I getting the right answer. The way that I solve these or approach these is you'll see that I have a library here that has all the days and their solutions. I have a test project that tests against some of the smaller examples. Each day gives you a smaller example with an answer so you can see if you're doing it right. Though that also gives you a false sense of security, at least it did for me, because sometimes I would solve the smaller one and then I get to the larger one and I would see I've made some assumptions that don't work anymore. But I have tests here. I also have an application that I run all these with all of the input files for the true problem that you're trying to solve. In retrospect, I probably should have done this all as tests, including the ones with the larger data sets to answer them, but that's the way I've laid these out. I also did a couple of performance investigations, although as you can see, I only went up to day 6 and I stopped just because the problem started getting harder and I didn't want to spend so much time trying to optimize things. I'm probably going to look at doing some episodes where I've made notes about places where I can optimize some of the later problems, and I'll do those as separate episodes. So without further ado, let's get into each problem. And by the way, before I start all these problems, I have to be a little bit careful because if I do scroll through these descriptions, they have the answers in them now showing up. So I don't want to show that. So I will hopefully try to remind future Jason to put something over the answer if I inadvertently show it here. Okay. So the first day is all about calorie counting. You get an input where you just have digits in groups that are separated by empty strings, and you have to find the ELF with the most calories. So originally I did that by keeping track of all the elves and then finding out which one had the most calories. This worked, but this is also a reminder that you really want to read the problems carefully so that you are only keeping track of the information that you need and that you don't try to keep too much around. In this case, I didn't need to keep all the elves around. I could have just, as I did here, keep the highest calorie value and keep changing that as I find a new summation of an elf's calories. And I also had to remember that when I get to the end, well, I may have parsed some of the last elf's calories, and so I need to do that check there as well. But this one was a little faster. And then for some reason, I didn't understand right away that each day has 2 problems or 2 parts. So the second part was you wanted to find the top 3 elves and sum their calorie values. So that's what I did here. In this case, I use a list because I was already, I think, like by day 15, that's when I finally realized this, and I was starting to just get tired of solving these a little bit. So I went back to just simply using a list and doing an order descending, take 3, and just keep the top 3 there. So not the most ideal way of doing it, but it works. And the way this works anyway is I'm only keeping 3 values in the list at all times. I'm just using some link stuff, which probably isn't the most optimal way of doing it, but again, it gave the right answer. Day 2 is rock, paper, scissors. You're given input to say what is being played, rock, paper, scissors, that game, and then your response. And in both parts, how you interpret the response changes. Okay. And then you have to basically figure out, based on what you're seeing in this file and how your responses are, what the final value is that you're supposed to give back. So the way that I did this one, if I go to actually 2 here, the thing I want to point out here is it wasn't too hard to say, well, if the opponent choice is a rock, then in one case you had to interpret the response to it and what that should be. You'll notice here that in one case you interpret it as a choice, and the other case is an outcome. So it's just a different way of interpreting the data. But I decided to pick just constants here rather than using an enum. I struggled with this a little bit. I find enums to be a little bit of a paper cut in C# because of the way that they're handled, especially with mathematical calculations. You have to cast them and then cast them back. And it's always felt a little klutzy with enums if you handle them that way. But you get nice IntelliSense here. Like if I just do choices dot, that kind of works. You get, choices dot, and then you will see the answers here. So it's a little bit nicer. It was mostly an experiment to say, hey, let's not use enums. Let's just use constants and see how this works. One thing too that I'm been glossing over a little bit just in these first 2 problems is you're always giving input and you have to parse that input. So how I parse those inputs obviously varies with each problem that I'm getting. And like you see here, run, I'm just basically splitting, and the first value and the second value are either an XYZ, A, B, C, and then I have to interpret those values correctly. The problem with constants too is that you don't get any type safety, but with enums you can get around that because you can make an enum set to a value that's not even part of the enum definition, so whatever. But the parsing always changes, and in some cases it's a little bit easier, in some cases it's harder. In this one it's pretty easy, in other ones it gets a little difficult. Day 3, you're given a whole bunch of what looks like random input, but for the first part, you interpret each line and say, divide it in half, what's the common item in both sides? So what's the common character? The second part is you have to look at a group of 3 and say, what's the common character between all 3? Okay. Now this one was interesting because this is the first time I purposely have ever tried to use a span or a read-only of span. And I did it just to see if it made any difference with optimizations. I did find out that it can help a little bit with speed. So it was mostly just an experiment to purposely try to use spans. When spans were first introduced in C#, they felt a little jagged, a little pointy because they weren't pervasive in the API. You're seeing that now in the APIs that are produced in .NET, where you can use spans very easily. As you can see here, I can slice and dice and do all these things with ranges and indices and whatnot. And it's much more fluid. It's much easier to use spans, again, because it's not like this bolted added on thing. It's now become more pervasive in the framework itself. So this problem wasn't too hard. You just have to parse the input correctly, and then also find when you're trying to find that common item between 3 rucksacks, how do you do that? I may not have been doing it the most efficient way, but the way I got it to work does solve the problem. So day 4, you're given 2 ranges on each line. The first part, you need to find out how many of those pairs have a range that completely closes another. And the second one, you have to find out when you have ranges that essentially intersect with each other. And this was an interesting one because I decided to use my library Spackle, which I had introduced a range type before C# introduced range and index into the language. And it started getting me into this weird state with ranges. If you've been watching my videos, you can see recently that I've been doing some work on ranges, and it's in part because of this work I did on Advent of Code, which was to basically use the range type and find out when something was intersecting or when it had a part of it or whatnot. So that actually made this problem not too hard to figure out because I was using that type. But this work was good because it had the side effect of making me really think much harder about my range type, and that it really shouldn't be based on the range type in any way, shape, or form, or have extensions on the range type that exists in .NET, because that's used for a very specific purpose, which is to do ranges in an array or something that can be indexed. So I'm moving far away from that now with my own range type to do some other things that are meant just to be for a range of numbers and not necessarily something that has to do with slicing and dicing an array. Day 5, as you can see from the input down here, you're basically given a stack of crates and then instructions on how you move the crates from one to the other. In the first case, you're moving them by picking up the topmost one and putting it onto the stack that you're supposed to put it on, and so on. In the second part, you basically just pick them all up as they are in that order and then put them down on the target. So you have to change, or using stacks or queues, or how do you pull things off. So this was mostly just work on getting the stacks and queues and data structures correct. This is also a little bit of a challenge in terms of parsing the data, because you had to parse it correctly and interpret it in 2 different ways. One was the initial stack arrangement, and then the next one was actually doing a little bit of a simple interpretation of the move instructions. Okay, so, and you had to figure out when you got the blank line, because that was your demarcation point between the two to say, this is determining how I should configure my stacks. And then the second one is telling me how should I move the crates. So for example, if I go to move crates, you can see I'm just doing a split on it on the code, and I'm parsing out what I think the tokens are and figuring out then how do I push onto my stack the value for that thing on the stack. Okay. And you can see sometimes I'm doing move crates or I'm moving them as is, which is the second part. Okay. So each of these are done a little bit differently. This wasn't too hard, but I have in my notes here that like for move crates as is, I was doing the last for loop on the count of the temp stack, and that wasn't correct. Reverse stacks, that was wrong. Get message, I had to order the pairs by key value. So if I go to get message here, I was doing something, order by the key value. So it's not by the, this is a stupid mistake in retrospect, but when you have a dictionary, it's just keys. They're not in any particular order. And I was just assuming, oh yeah, they're going to come out the order I put them in. No, you actually have to order them by the key, and then that's how you get them in the order that you want it to be. So a couple of kind of boneheaded mistakes I made on this one that in retrospect, I'm like, why did I do that? But again, that's why you write tests, because that would uncover these things and I would go, oh, that's where the problem was. That's also why I tried to structure a lot of my solutions in most of the cases, not all the time, but in somewhat simple, digestible code, because that made it easier for me to track down where the problem was if I did have an issue. So day 6, you're given some random input. I am just being careful with what I'm showing. So you're given a line like this, and you need to find the position where you get 4 unique characters. So that gives you a marker. So in this case, down here, it says first marker after character 5. So 1, 2, 3, 4, 5. I think that's saying this is the first place where all these characters are unique. And then the second part is it's the first 14 characters. The thing that I realized with this one is I was storing these, I believe, in a way that basically, you have a marker here, and then do you find a duplicate or not, and blah, blah, blah. And then I realized you don't even need to use an array. What you can do is essentially use a bit mask, and that's what this marker mask is. Because you're going through the characters and you can say, well, A is the 0th bit, B is the first or second bit, and so on. And so you're trying to find, did I flip this bit or not? And if I had before, then I need to turn it off because, or on, or however I did it, to make sure that I found a duplicate or I didn't. Okay. And this was faster. If I look at my code here, or my results here, doing it with an array compared to doing it with this bit twiddling thing, it was, the array was 45 microseconds and the bit twiddling was 31 microseconds. So this is a nice reminder of sometimes you can optimize things in ways that may not be as obvious, but it does make your code a little bit quicker. Day 7, you're basically doing a emulation. Took me a second to think of the word emulation. Emulation of a file system. And for the first part, you need to find a directory of a certain size, but no more. And then the second one is you need to find a directory that you can delete with another condition. But the big thing is finding the right abstraction for this, for how I declare files and folders and all that other stuff. And then how I discover this output based on like what directory I'm moving to, what's the contents of that directory, and so on. So what I did is I first just created my own abstractions down at the bottom here. I had this thing called a document. I didn't want to use stuff that was in system.io. So I had my own things like a document, a folder that was recursively containing documents and other folders, and then using that to figure out how I can enumerate them and how I can add folders to things and how I can get the size of a folder, because you had to get the folder size recursively and so on. So this just was that. I think that was the biggest part, was just getting that structure correct. And then somewhere in here, I'm also doing the, here's where I'm trying to figure out that root folder. And that root folder is found by doing all the instructions. Is it a command? Is it moving to a different directory? Otherwise, all the things that are grabbing the, what I call enlist mode, these are all the files that are coming through. And then I can get the either if it's a folder or if it is a file, and then interpret those results correctly. So that was the biggest part of this problem, is just getting that structure correct so I could get to the right answer. And also using longs, because you can't use ints. This becomes a thing in future problems where you have to use larger data types to store your numbers, because they would overflow if you use something like an int. This one, you're given a grid of data that gives you the height of a tree in a grove. So you can see here 3, 0, 3, 7, 3, and so on. And the first part is you're looking outside in to see how many trees you can see. And then the second part is you're in and you want to find the one that gives you the most scenic view of the most trees. Which position is that? Okay. And so the way I did that is I just created a multidimensional array, which, as I was doing this problem, I thought, this is, I think, the first time I've legitimately used a multi-dimensional array in C#. I've known they've existed. I've just never run into a case where I actually needed to use them for whatever reason. I don't know why. It struck me that I went, yeah, I don't think I've done this before. So I was able to just use the multi-dimensional array that, in both cases, with getting the visible tree count from the outside and then the scenic score from the inside out, and then just use the rules that the problem gives you to say, look in each direction and find out what those scores are based on the rules. So this one, really, there wasn't much to it. It wasn't that hard. I may not be doing it the most efficient, effective way of doing it. There's probably ways to optimize this to say, if you've already done one location and figured out its scores, then the next one you don't have to figure it out because reasons, but this worked and it was fine. Day 9, rope bridge. This one was hard for me. This is one that I tried to do as soon as the problem came out, and that was a mistake because I got very frustrated trying to figure this one out, especially the second part. And I just could not get this. So I finally got it the next day, but I have these blocks, these wooden blocks that I've been meaning to do a project on for a while and just haven't gotten around to it, but it was in my office. I was literally on the floor moving these blocks around, trying to figure out, if I go in this direction, then how do the other parts of this stake, I know it's a rope, but how do they move based on how the head is moving? This just took me forever to get my head around. And the solution is probably not the best at all in terms of which direction I'm going, and then how does the head affect the tail and the other parts to it. I don't know why. Just something about this really threw me for a loop. And yeah, this second part here, that was the one where this was done for part 2, and I don't even know if I can explain to you what I was doing here. But this is the best way that I could get it to work, because as you got this rope that got longer and longer, and you would move around and through it and around, that kind of change, even though as you were going in one direction, it thought it was going that way. And yeah, I got really messed up with this one. This one to me was probably the hardest out of all of them, just because, again, I try to do this fast. That wasn't the right way to do it. And it was a problem that my brain just couldn't parse. I couldn't get the rules right. Fortunately, I finally got this. But yeah, this one was probably the most frustrating out of all of them for me. So day 10 is basically emulating a computer. You have a bunch of instructions here that tell you how you change a register value and how many cycles it takes to do this and when the things change. And so there was a little bit of care that needed to be done here in terms of how do you update values and when you do them. And then the second part adds in a display or a CRT that you update based on what the values are and whether the pointer is at the same part of where your register value is. But if you look at the code that I have here, it's really not that much. It didn't take a lot for me to figure this one out. The things that were tricky about this were, again, the ordering of instructions and when you do things and in what order do you do them. Like with this CPU, that when you got an instruction, when you draw the pixel, when you update the signal strength, does the instruction start with this? And then the display was just a bunch of characters. And so then I just printed that out if I run the solution. So that made this, it was tricky getting some of the coordination correct, but as you can see, there really isn't a lot of code to this one. It ends up being kind of a succinct problem. Day 11 was a little hard, but fortunately for me, because of the work I had to do on my master's thesis, I was able to see the trick for part 2. And I know a lot of people, I have read the subreddit, because there's a subreddit for this if you want to look at what other people have done. This one seemed to throw a lot of people, because the first part, you're given a whole bunch of instructions about how monkeys pass things to each other and how you basically interpret that and how worried you are and all this other stuff. That wasn't too hard. The second part, though, it takes away something where you're dividing your worry by 3. And so it essentially makes the accumulation of the answer grow wildly. And you can't use an int, you can't use a long, and even if you use a big integer, the time it takes is just astronomical. So you have to find a way to keep the number small. And a friend of mine who is doing this too, not the guy that I work with, but another friend of mine, he's been doing this and he's like, I cannot figure out part 2 of day 11. And the trick is, at least for me, the trick was noticing this divisible by 23, divisible by 19, that these are primes. And I think somewhere down below there is has relief, I think, or range. Yeah, range. I think that's what I'm using here. I basically mod by the range, which is a product of all those primes. I think you can actually do it just by the prime for each one. I'm not sure off the top of my head, but this one definitely worked. That kept, and it just mathematically works out that way to keep the answer within a given, if there's a ring or field, I don't remember, but that worked. But if you don't know that, you're screwed. The problem itself isn't that hard, but it's that the data representation, you can't handle it, and it becomes so big that, like, my program just came to a crawl. So this is the first of many indications on a lot of problems that you have to know some optimizations so that they can actually run in a reasonable amount of time. And I think this one, even though it wasn't that hard for me, I could definitely see where this would be hard if you didn't know that trick. You would have just been literally stuck and you would not know what to do. This one is literally what it says. It's a hill climbing algorithm. The chart that you're seeing here basically says I'm starting here at S, and then as the characters increase, like A is at this level, then B is 1 higher, C is 1 higher, D is 1 higher. So you can only go from an A to a B. You can't go from an A to a C or a B to a D. You can go down as far as you want, but you can only go up in increments of 1. And so you have to find the path that gets you to E and the shortest way to do it. And then the second part is, well, if I started at any A, what gives me the shortest path? So there were definitely things I had to do to keep the search to a minimum, especially for the second part. So as you can, again, the code in here just basically has ways to map through and keep track of where I'm going and which direction can I go. And of course, if you're trying to find the optimal solution, you can start to find out a whole bunch of different paths. But then I realized the first part is not too bad. The second part, I had to realize that you may cross a path that you've already hit before. And so you can prune those down here. There was here I have to prune the path. So I have to find a way to say, if this path runs into a path that currently exists, that means, I forgot the logic I had around this, but that basically means this path, one of the paths can go away because it's not ideal, it's not optimal. You would have run into that location anyway. So you want to pick one out of the two. And that made this reasonable to solve. Again, this may not be the ideal or optimal way of doing it, but it got me a solution. Day 13 is Lisp, sort of. You're given lists of ints, and depending upon how they're grouped, determines how you compare one to the other. And you have to determine how many of these pairs of packets are in the right order. And then the second one, you have to order all of the lists with two specific lists in a certain place, and that gives you another number. So you have to compare these as saying, well, if this is just a number, but this is a list of numbers, and this has to become a list of a 9, and then the 8 can compare to the 9 and so on. So what was interesting about this for me is you could do things like you can do a compare here. You'll notice that I have a get correct pair sum here, which takes these this input and creates the left and the right, and you can compose them. But then because this is a list of object, I had to have lists that could have lists of objects, and those could have the ints. I wish there was a better way that I could think of doing this. But the cool thing about all of this is once I got all the logic in place to say, how do I compare a list to a left to a list to the right, by if one's an int and one is not, or it's a list of objects, and how do I change those, and blah, 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 is that for the second problem, all I had to do was say sort all of the packets that I get based on this comparison function that I had created before, which is down here. And so that made the second part actually really easy to do, because I just added in these two divider marker packets, and that just became part of the solution. And then I just said, here, that's where they are, and I give the answer back. So this one actually wasn't too bad to do. This one I remember being kind of fun to solve. Again, because the second part, I was able to use something I did in the first part, and it made it very simple to solve the second part. So day 14, you're basically given input to say, well, you're having sand come through and there's rock structures, and when does the sand actually pile up to the point where it's going to fall down infinitely? But then the second part is, well, no, there's actually a floor. So when does this all pile up to the point where it gets to the top and it stops, or something like that? So this problem, I saw in my notes, it wasn't too bad to get it for like the abyss path, where in the first part you assume that once it falls down, it just keeps falling down, it won't stop. The rules weren't that hard to encode and to do. The one where you have the floor, this was just, again, following the rules about where the sand will be, and then as it builds up, and then, you just basically, once you get to the top, then you're plugged and you can stop there. Okay. So you have to interpret the map that you're given. You have to get the rocks, and, this all wasn't too bad. But in my notes, this was the funny thing, is at some point when I was solving for part 2, I got parts 1 and 2 screwed up. They were mixed up, like my implementations, and I had completely messed up. I hadn't committed my work. And so I had to basically, I think, start all over again. Yeah, what did I say? Oh, part 1 was wrecked. So and I have my notes here. I still don't know how I did this. It was something that I just wasn't awake enough to realize what I was doing. But I eventually sorted it out, no pun intended, and I figured out where sand was going and how much. So day 15, you're given this configuration where you have sensors and beacons, and a sensor is able to find the closest beacon. And so you're given a configuration that starts looking like this, and this sensor, that's closest beacon is this one, I think, and you're given in the first part to say in a line where is a spot that is not covered or something like that. And then in the second part, it's the whole range of sensors and beacons and what they are circularly enclosing, and there's one spot in that whole grid, that's where the distress beacon could be. And I remember this as I'm looking through my notes, that the first part wasn't too bad. And which one is the non-beacon locations? Yeah, that's the first part. That wasn't too bad. That was just going through a line and saying, could a beacon or whatever that is be here or not? The parsing part wasn't that hard either. Now, the last part, though, the second part, you have, like, I think it's, what do I have in my notes here? It's just too much. Whatever the input is, if I actually go to, what is it, day 15 input, Yeah, you don't see it, but these numbers are just huge. So if you're thinking of a grid that's big, you can't do that as an array because there's just too much to look through. And you have to do it in a smarter way. And so I think what I ended up doing is I would start going through it, but once I hit a spot where that was being enclosed by a sensor beacon circle, I could move all the way over to the end and then go to the next part. Okay. And so I could probably do this even smarter in terms of figuring out all the areas that are being enclosed and doing some fancier math or something like that. But this got me the answer in a relatively short amount of time. This, again, was just one of those spots where you had to realize you couldn't brute force this. You would have just completely run out of time. You couldn't also create an array to allocate all this because it would have just been huge. You had to be smarter with the input and figure out what you're given as data and how to traverse all the information you're given in a efficient way. So this one was fun to solve. I remember spinning my head a little bit on this one and then trying to figure out, well, how can I figure out how to optimize these things? So yeah, I enjoyed this one. Day 16, I felt was a traveling salesperson problem because you're given a grid of rooms and tunnels and flow rates, and you had to find out how to maximize the amount of flow that was going through in like 30 minutes of time. And so there's all these different possible paths that you could go through, and you could backtrack, and you had to figure out how to basically get the most flow. So I felt like this was something that would wildly spin out of control. And I did put in, I think you can see here in my code as I'm going through all the possible paths and when I could make a new path, and I also had to keep track of, well, if I go into a room where the valve is already open, you don't try to reopen it. It's already open. You don't shut it off. And then I do this complete guess. I just basically say, if I've hit 50,000 paths, then I prune it by saying which ones are giving me the most pressure, because those are probably the ones that are going to give me the best output. Again, there's probably better ways to optimize this, but that's what I did for this problem. And then I just picked the max one, and that worked. The second part of this is you have these elephants, and if you train an elephant, both you and the elephant can now start running around the maze and turning them on in parallel. So I had to be a little bit smarter about the elephant paths that I have. And yeah, I have a path and an elephant path. And it definitely gets a lot harder, or I should say it becomes more difficult, because if you're both in the same room and one's open, or if you're in different rooms, or one, you had to keep track of a bunch more states in terms of what the human and the elephant were doing. And then of course you're also making more paths as well. So there was another time where I had to just put in this guess of saying, well, 50,000, and we'll just stop there and only pick the ones that have the best pressure. But this ended up working. So yay, it works. Day 17 is Tetris. You're basically playing Tetris. You have 5 different rock configurations. You're in this like long, tall cavern that's 7 blocks long. And then you're given this cycle of jets that are pushing the rocks back and forth. That this also cycles. So once you get to the end, you start again, and you stack the rocks based on when they hit the floor, or a rock that doesn't let them move anymore. So you're basically playing Tetris. And the first part of the problem was you do this for 2022 rocks, 2022. The second one, for whatever reason, it's demanding that you do this for 1 trillion iterations, which again, that's an indication that there's no way that you could let this run for 1 trillion iterations. Even if you had something that could let you do 1 billion iterations of these rocks a second, it would still take a fair amount of time to finish. And so part of me said, okay, again, what's the optimization here? And the thing that I thought of, again, is this kind of ring field circular thing going on, which is the jets here will eventually wrap around. So it seems like at some point the rock stacks are going to get to be cyclical. They're eventually going to repeat. And so once you find that repeating structure, then it becomes, aha, I know how high it is. I know at what point that happened. And so I can basically just add on virtually a whole bunch of these and then figure out what the little top part would be at the end. And so that took some time. I mean, if you look at, there's notes I have in my repo and you can find for day 17, there's definitely a lot of notes here to figure out how do I find that cycle? How do I figure out then how tall that whole big rock structure is? And then how do I do the math correctly so that I can get to the end? Even with that, I think this took some time for this to run with the big data set because of just how long it took for it to cycle through. But once it hits that cycle, then the problem essentially stops because the rest of it is very simple math and it's done. So this didn't take hours to run, but I remember this taking a little bit of time to finally get to where you figure out what the cycle is. And again, there might be some cute math that you can do where you don't even have to run that simulation to find out that first cyclical big piece of rock. Then maybe there's some easier way to figure out, oh, this is now where this is going to start cycling, and I can just move up and figure out the top of it and then move on from there. But again, at least I was able to figure this out so I could let this run and then come back and then see the answer. Day 18, you're basically given a 3D structure of a bubble that's used with little cubes and given by coordinates here. I think I just showed the answer. So Jason, don't let that show up. But you have to find the outside total surface area, I think, or something like that. This one, the first part wasn't too hard. The second part is, well, now you have to actually figure out what is encased within the bubble. And so to figure out what coordinates or what was air and what was inside the bubble and what wasn't, that took me some time to figure out as well. But you can see here just by the scroll bar on the right, there's a lot of code here that I did. Probably wasn't efficient, but I had to do something where you can see here in my comment, which is trying to figure out, was this an air bubble? And you had to, if you're thinking in 3D space, was this a bubble that maybe like went around and it's in some corner and, well, it's like it's all encased here except in one spot. So then you have to go out that way until you hit a wall and then, go out that way. And so once you figure out what's actually encased within this whole rock structure, then that was fine. But again, that took some time to get that correct, to get rid of all the air bubbles external from the cube. And if I remember right, on the subreddit, there are people that actually graphically showed what this looks like, which I figured you could do. I just didn't want to take the time, but people just drew this out, and I'll try to remember to show some pictures here of what this structure actually looks like, which is funny because I explained it to my wife and she's like, why wouldn't you just draw this out? And I'm like, do you have any idea because she's an artist, and I said, but do you have any idea like how long it would take to just physically draw all these out? And even if you did that, to manually then count all the surfaces, that would be incredibly long. That's the power of computers, is that it does that and makes it simpler for us. Day 19 is another sort of optimization problem because you're given blueprints for how different robots can construct other robots to do resources, and you basically want to get geode robots because those can create geodes or crack them open, and you want to do the most of those. And then the second one, you have more time, but then you have to do some other optimization. So this one, mostly the bulk of the work was, I think I had something in here that parsed the input. Did I? I don't remember. Did I actually do something here that parsed the input? Yeah, I didn't. I had to read all these and put them in. For whatever reason, I was lazy and I didn't come up with a parser for this kind of input, which again, now in retrospect, I could look at and say, does the line start with blueprint? What's the number? And then what robot costs what ore, because all these obsidians always have ore and clay, geodes always have ore and obsidian. So I could write a parser for it, but I just was tired or something. So I decided not to do that. But this one again is you want to find optimum paths. And so I basically said, can I create a robot of a certain kind based on resources that I currently have, or do I just mine and build up my resources? So you need to find out the best path of mining and creating a robot, because creating a robot takes time, but then that gets you to the next level and so on. And I put in another constraining factor here to say, If I get above 75,000, obviously the target is to get the most geodes. And to do that, then I need a lot of geode robots, which means I need obsidian mined with obsidian robots and so on. So that's the ordering I did to say get the ones that are getting me to that ideal path. Okay. And that's how I solved this. So I think with both of these, yeah, the time is the only thing that changes, and then the quality level, or however you quantify the answer, changes a little bit. But the way that you go through the paths in both of them is almost identical. In fact, they are identical. It's just more time with the second one. So anyway, that's, yeah, and then that's right too, because with the second part, if I go back to program here and go down to where I'm doing this, yeah, you only do the first 3 blueprints. You don't do, because you're doing 32 or something like that. So, but same algorithm to solve the answer. Day 20 was fun because you were given an initial input that said, how do you move these values around each other? But you had to keep the initial arrangement the same, because the number that was being moved around was based on where it was initially. So you had to be a little careful about keeping track of what the original sequence looks like to move the things around. This, and including the second part, which made things that much more harder because you had to cycle a lot more or something like that. But the ending code wasn't too bad, because moving things around and being able to look back at where it was in the original list. The thing is using mod in C#. If you do -11 mod 7, it's not giving you I think it gives you a -4 back. And what you want is a 4 back or something like that. The point is the mod in C# doesn't really work with how a mathematical ring or field or whatever it is would bring you back to, because a -11 should be 1174, should be a 3. That's right. It shouldn't be a -4. It should be a 3. The second thing that I was forgetting is I'm moving things around in the array and I'm doing a mod. I can't include myself as an element because I'm kind of pulling myself out. So it's 1 less. And so I had to be a little bit careful in terms of when I'm doing these mods with the length and how I'm moving that. Like you can see here, length -1. It's not always being done, but we had to move and how much you're shifting. That's when it mattered that you had to do a length -1. And once I figured that out, then I finally got the right answer. Day 21 is math, especially symbolic math, where you're basically given a bunch of expressions like this, and you have to figure out the root answer. And some of these are constants, and some of these are using the variables for the constants. And so you basically had to do a bunch of expression evaluation to get to the root. The second part says that the one variable, I think it's, yeah, this one, human, is actually a variable. It's not a constant. And so now you have an expression that has an unknown variable. So to do this, if I'm looking at my notes here, if I remember right, the first part, this is one that I actually tried to solve as fast as I could as well. And so I just blasted through this one as quick as I could. I didn't even write tests for this right away. And I got the answer right away. I was shocked. I ran this and just said, seems to work, and gave me back the right answer. But it took me like 25 minutes to finish it. And I saw the leader was done in 2. I'm like, I'm just not a fast developer. Yeah, like I don't get any of this. So whatever. Was able to solve these. The second one was harder because you actually have to solve for a unknown. And I am just not smart enough to figure out how. I was able to figure out the logic of keeping the expressions with the variables and building up that final expression. But what I ended up with is something where you have an X and a Y, and here's the result. So this is the left expression. You can see here's that variable there, and then this is the right expression. So you have to say, how do you solve for this? And I used Wolfram Alpha. Now, the right part wasn't too hard. I just plugged that in, and it gave me the answer. This one, this was too big. So I had to start picking out enough of the left-right parenthesis matches and then keep that around and then solve for more of it and more of it and more of it. And then I finally got to the point where I was able to solve for the whole thing. So still using code, but this was the one spot where I went a little bit beyond what I was wanting to do and solve that variable myself. Maybe there's a smarter way to do it, but this worked. Oh, day 22. The first part was pretty easy because you're basically given a map and you start at the top here, and then you're told you're going to the right. And if you hit a wall, you stop, and then you're told to turn right from where you currently are, and then you go that many, and then you go left, and it just basically wraps around. So it's a 2D map. That wasn't too hard. But then the second part says, no, that's actually a 2D projection of a cube that's been folded out. And so if you're moving off the edge, it just doesn't wrap around. It could go somewhere else. Okay. What I ended up having to, in fact, I avoided doing the second part until I finally finished everything because I couldn't see if, and there probably is a simplification, an algorithm just says, oh yeah, if you got this, it folds this way, and then these edges go off that way. And I'm like, no. What I did is I basically did something like this. So I actually took this Rubik's Cube, a 5x5, laid it out here, and then just took this is from the big problem, and said, okay, well, they're all 50, and this description says that's what it's doing. And so then I would fold it like this to where you got it as a cube. Okay. And then I just had all the numbers marked here. So I'd say, well, if you were moving like right off of 1 here, this edge, well, where does that put you? And that makes you go to 12, except you'd have to be going left on 12. And so then what do your new coordinates be? Or what are your new coordinates? Wow, did this take me a long time it wasn't hard. It was just very, very tedious to get this to solve. And the code here actually is not too bad because what I say is, just give me a function that maps all this. And then it's simple, right? And it actually is. The second part to mapping for a cube is actually not, it's less code because you're basically saying the mapping function is going to tell you where to go. The first part, you could map off into what was a blank space, or you could map off to what is index out of bounds, depending upon which directions you're going. You had to be a little bit smarter about this. This one, the mapper just says, here's where you're going to go. You just have to figure out if you hit a wall or not. But it was creating that mapping function, which I believe is in the application for day 22. Yeah, so this is my mapping function. This huge, big thing that says if you're moving off an edge here, then you're going to go into this new direction that way. Pain in the butt to do. But when I solved this was actually the last star that I needed. And this was very satisfying to finally get right. Again, probably not optimized, probably not generalized, definitely not generalized, but it worked. Day 23 was pretty straightforward. Just took a long time to finish, and I couldn't figure out, especially for part 2, how to optimize it. So you're basically given an initial configuration of elves, and they move, but they only move like out. So it's like this thing that's like kind of growing, and then eventually for part 2, it will stop at one point. Or I'll explain that in a moment. For first part, you basically run the simulation for 10 moves, and then you say how many in the maximum rectangle that it's in, how many empty squares are within that. That wasn't too bad. If I look at my code here, I think, yeah, the no movement turn was a little different. The empty ground tiles was pretty simple. You say the elf proposes to move to a spot, then you execute those proposals, and then you rotate your directions. And I think all that's encapsulated in this proposals class that I have to say, can you move because nothing's around you, and what direction you're going, and which, then it proposes a direction that you want to go to, and so on. So encoding all that wasn't too bad. The second part, I remember taking a fair amount of time. If I remember, yeah, it took a long time to get the answer. This is one of those that I just had to say, you have to figure out when a move happens where none of the elves have proposed a move. They're all going to stay in one spot. So what's the turn that happens on? And so this wasn't hard to do. You just had to get that turn value. And this, again, took a long time to where it finally diffused to a spot where they all stopped moving. And that's the answer that I'm giving here. So I think this is one I just let run and come back later and say, oh, it finally gave me an answer. And I was also printing out here like what turn, how many have not proposed a move to a different location or something like that. So I was just watching that finally start to tick down, down, down. And I'm like, good, it's going in the right direction. This one is basically, you have these blizzards, which are determining which direction they're pointing. And if they hit a wall, they just magically produce on the other side, but they're always going in that direction. And you start up here and you basically have to find the path to get down to the bottom and the fastest amount of moves. So you don't care about what the path is. You just need to find out what path gives you the minimum amount of moves. And you can decide to stay at a location, or you can move to a location as long as a blizzard is not going to end up at that location at the next turn. So the first part wasn't too hard. You just basically say, once I get to here, and in fact, in my code, I actually took out all the walls because I knew you're starting here. Okay. Well, come on, highlight. Jeez, that one. And once you hit here, then you knew that the next move was you could go right down and you're done. Okay. So I took all that out. You have to be a little bit smart to say you can only enter the grid once there isn't a blizzard here, because the real pattern has got a lot more blizzards and they're all moving around everywhere. But to find that minimal path actually wasn't that hard, because what I realized when I was debugging, because I thought, oh, I'm gonna have to start doing like pruning like I've done before. And I'm like, no, what I realized is that you can end up having paths that, because one's staying at a spot because they can't move anywhere, that another one ended up at that same spot with the same amount of moves. That's essentially a duplicate. You don't care how you got there. You just got there in 3 moves. So you could remove those. And that made the first part really simple. The second part, you have to go to the end, but then you realize you need to come back again, and then you need to go to the end again. So I needed to add in this extra logic to say, did you make it to the end? Did you go all the way back to the beginning? Because then once you finally get to the end, that's the one that matters. And that one it took some time to code that up. I think the thing though that I had to realize is, where is this? Yeah, full expedition, because you could go back and you could finish. But when you go to the end the first time, I was keeping my expeditions at that end spot, and that was wrong. They actually move off the grid. So I had to put them in a bucket here and then do the reverse. Once the blizzards weren't in that spot, I could move back up again and start going back and trying to hit the top part again. And then I go in to go finish expeditions. And once I could move down, because there's no more blizzards there, I could go back down again. Yeah. So I had to put all of that code in here to say, not only could it be in direction, but could it move off the board and could it come back on? And did it reach the end and did it reach the beginning? And then I could finally say, and you notice I had a pruning size here and I was doing this, but once I realized the duplicates weren't in play and I could just remove those right away, then that made this go much, much faster. And yeah, that made this one fairly easy to solve, but it took some time to get to that final state. And the last one, this is only one part, day 25, full of hot air, snafu numbers. So you're given a number here that's in base 5. Okay. You think it has hexadecimal numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A is 10, B is 11, and so on. It's just a different way to represent a number in base 16. This is using base 5, except it's not 0, 1, 2, 3, 4. It's -2, -1, 0, 1, and 2, where the -2 is represented by an equals, 2 negatives. A -1 is represented by a dash, 1 negative. Okay. And so you need to basically add up all these numbers and give back the number as a snafu number. Okay. Going to a decimal is not that hard. That one is basically, okay, what's 5 to the 0 times 2? And then you add 5 to the 1 times -1 plus 5 to the 2 times 0 plus 5 to the 3 times -1. And you just add all those up and then you get the decimal number. So adding these all up as decimals, that conversion was easy. Going back to a snafu number, wow, did that take me some time. So here's what I did. I couldn't figure this out. I'm like, how do you go backwards? Especially when you have negative parts to this. It just kind of blew my mind. So I sat there and looked at it. I'm like, how do I do this? And I finally just wrote out some of these numbers, and I started to see a pattern here. For positive numbers, you basically figure out what's the largest power that you need to represent that number. Okay. And you see the pattern. What I eventually realized is once you have that first positive number, 1 or 2, you can go into the lower bound of it because you know now what the first number is going to be, a 1 or 2. And then the previous parts to that will repeat, -2, -1, 0, 1, or 2, but they're going to do it like here. They do it 5 times. And then the next one would be 25 times. And then the next one would be 25 times 5, that many times. And so to go from one to the other, like I have translate the decimal, that's easy. Okay, that's not that much work. Translating it back to a snafu number, I had to do a little bit more work to figure out, well, do I have a 0 and 1 in front? And then I have to now I had to do these ranges because I hadn't published my new version of Spackle where I can do on any number, like a big integer, come up with these ranges and partitions that I needed, the partition size, and then say, well, does that number in that partition of 25 -2s or 5 -2s, and then I could add that as a character to where I finally was able to get down to the part where I had the whole number, and that worked. So that probably was a little bit confusing, but again, it was because I saw this pattern, and I think the pattern goes in reverse. So in other words, if you wanted to get a -3, you figure out what 3 is, and then you just flip the character. In other words, this first one was a 1, it's a -1. This one is a -2, it's a 2. And you just would flip all the characters. So I think that's how it would work. But you didn't have to do that. There was just one part. I was anticipating the second part would be like, give the negative version of this number or something like that. And I was like, aha, I'm already ahead of you, but it didn't happen that way. The second part is you just need to put all your 49 stars in, which made me forced to figure out the cube mapping. And then once I was done with that, I got to that whole thing where I could see the chart with all the balloons flying off the mountain. So what do I think about Advent of Code? Overall, it was a lot of fun. Frustrating at times, sometimes kind of difficult for me at times, but very satisfying. It refined my skills in C#. It made me solve problems that I haven't tried to solve before. And I think that was good. I think it was a good refresher of my skills. And I'm glad that I did this. I'm thinking maybe in the future I'm going to pick probably the previous years, maybe do one of them in C# again, but maybe pick one that's in a language I don't know and learn the language that way by trying to solve those problems. We'll see. I am thinking about in future episodes for FreeCodeSession to do some optimizations that I had mentioned before. I think I have in my notes here. I have optimizations for 15. That was, which one again? The beacon exclusions. I think I have some other optimizations I could do here. Parallelization, I think would be a good one. Day 24, where I have the blizzards. I'm actually keeping a list of chars for each location on the grid. You can use another flags enumeration and just flag when a blizzard has moved into that area or not. And that probably would make things a little bit faster too. So I'm thinking of doing those in future episodes to do. In terms of problems that were the hardest, the day 9 to me felt like the cube one was hard, but it was just a matter of getting all the mappings right. Day 9, I just could not get my head around that. That took so long for me to figure out how to move those stupid ropes around. It just did not click with me. Day 11 wasn't too bad, but I can easily see where if you didn't know the trick, you would have just been lost. You would not have been able to figure it out. I don't know how you would have been able to figure it out. So I think that one was probably the hardest from a community perspective. Maybe not, but I've definitely, not just with the friend of mine, but with other people I've seen on the subreddit, it really trips people up. So, but that's just what happens in your experience. Sometimes you just know things and you're able to get through a problem, and sometimes you don't know them, But at least with the other ones, even if I didn't know the right optimization, I was able to come up with something to solve it. Day 11, again, I don't know how you could solve that unless you knew that trick. It wasn't worth competing. The whole leaderboard thing, is just something that I find to be a personal waste of time. To me, it's not about trying to solve these as fast as you can, in part because I'm not that fast with this stuff. I tend to be more, I don't want to say thoughtful. That's not the right word, but a little bit more just trying to figure out what's the right optimization, what's the right way to do this, and then think it out. And some people, it just comes to them and it's no problem at all to come up with the answer. And I have a lot of respect for people that just have that ability. I don't, but again, this was more about trying to just take a problem and solve it and see what you come up with. And again, I think I was able to learn a lot. And from that perspective, I think that's why this was satisfying for me. Again, I may do this as other languages and try some out the other years. I'm not going to do another episode like this, but just to see what that's like. And in the future, I will be doing some episodes, a couple of them on some of these optimizations I talked about and walking through them and just trying them out and seeing, does it actually make a difference or not? So I'd highly recommend doing this. If you've never heard of Advent of Code before, give it a try, give it a whirl. It's just a way to hone your skills. And it's to me, a fun way to do it and to learn how other people have done things as well. Hopefully, if you've tried this, especially in C#, I'd be interested to hear what you've done and what you may suggest is going, Jason, you missed this, or you didn't do this quite right, or did you think about doing it this way? And constructive criticism is always helpful and encouraged. So you can leave those comments either in the repository as issues, or if you want to just put them down in the notes section as comments in this video, please do so. And I would really appreciate hearing what other people have to say about what I've done. So thank you all for watching. Leave comments and questions below. See you in the next episode.